Hello, Phi Squad. We devised a solution strategy that will enable you to solve every material balance problem ever. Practice problems are what solidify the concepts in your brain. The problems we are going to solve today show how our ultimate strategy works in practice. Our focus today will be on problem solving for material balances of the total system. We'll cover balances for individual components in the next part. You can find the notes from our previous videos linked in the description. Before we dive in, let's do a quick recap of the solution strategy.
First, we read the problem to understand the setup and the requirements. Then, we draw a diagram representing the system and mark all the known information about the mass inputs, outputs, and the accumulations. Select a suitable basis, then start writing the material balance equation algebraically for the total system and for each component. If we want to analyze what is happening during a process as it proceeds, we use the mass flow rate balance. If we are more concerned with the result at the end after the process has finished, we want to use the total mass balance. Both sets of equations are valid across both continuing and completed processes. It's just a matter of what is more useful. Figure out which of the quantities are known or computable with the known information and which quantities are unknown. Pre-fill any unknown quantities based on reasonable assumptions if possible. For example, we can assume the density of water to be 1 kg per meter cube if the density or temperature is not specified in the problem. Rewrite all the mass terms using the appropriate mass representation as we learned earlier. Substitute the numerical values along with the units. Now, ensure that all units are correct and consistent. Apply any conversion factors if needed. Finally, calculate the unknown quantities. Depending on the problem requirements and the basis we selected, we might need to scale our calculated quantities to obtain the final desired solution.
We have 5 ice cubes in a tub, each cube weighing 1 ounce. After 30 minutes, all ice cubes are exactly half melted, 0.5 ounce each. What is the mass in kilograms of water in the tub? You can pause here to try to solve it on your own. Let's draw a diagram for our system and mark what is given in the problem. Our system is the tub. Putting ice cubes in the tub is mass input. Any material contained in the tub is mass accumulation, and any contents being taken out of the tub is mass output. We can work with the quantities that are already provided and do not need to select a basis for this problem. Now we write the equations. Since we are concerned with the end result after 30 minutes and not how the result is reached during the 30 minutes, we will use the total mass balance equation instead of balancing the flow rate. Total mass entering the system plus total mass being formed in the system minus total mass accumulating in the system is equal to the total mass leaving the system plus total mass being consumed by the system. This is a physical transformation, so the molecules maintain their identity. Let's balance the H2O. Mass of H2O entering the system is simply the total mass of frozen ice cubes. Mass of H2O accumulated in the system is equal to the sum of the mass of the half-melted ice cubes and the mass of the liquid water. No mass is leaving the system, and no additional H2O molecules are being formed or consumed in the process. Thus, the equation becomes total mass of the fully frozen ice cubes minus the total mass of the half-melted ice cubes plus the mass of the liquid water equals to 0. The masses of the fully frozen and the half-melted ice cubes are computable, and we are left with one unknown variable and one equation. So the problem is solvable, and we don't need to assume any quantities. We will calculate the mass using the number of ice cubes. The final equation becomes mass of one fully frozen ice cubes times the number of ice cubes minus mass of one half melted ice cube times the number of ice cubes plus the mass of liquid water equals to 0. Let's substitute the numerical values with units. We will need to convert ounces to kilograms using the appropriate conversion factor. After the final calculation, we get the mass in kilograms of water in the tub after 30 minutes. Wait, what about the material balance for ice and water separately? Depending on the problem, you might not always need to write every equation. But if you are in doubt whether or not you should write equations for each component, it's better to write extra equations that may be redundant than to skip writing equations that are very much needed. We made a list of conversion factors you may use frequently in material balance problems, just like this table of mass representations we made. You can find both these tables linked in the description. A 1 kilometer long bridge has a single lane with a single entry gate. The entry gate lets in only one car at a time, and the next car is let in only when the previous car crosses the halfway point of the bridge. Each car, weighing 1000 kg, on the bridge moves at 60 kilometers per hour. Question 1. How many cars cross the exit gate at the other end every 5 minutes? Question 2. If 10% of the cars park on the bridge and stay there, how many cars leave the bridge every hour if the entry gate opens at the same interval as before? Alright, let's start by drawing a diagram of the system and marking the knowns. The system is the bridge, the traffic is the flow of mass. A car crossing the entry gate is mass input, a car crossing the exit gate is mass output, and a car on the bridge between the gates is mass accumulation. Let's select 1 minute as a convenient basis. Now we write the equations. This is not a multi-component system, so we only need to consider the total system. Since we are concerned with what is happening during an ongoing continuous process, we will balance mass flow rates. We will also need to use one of the equations of motion to determine the time a car takes to reach the halfway point, which relates to the input mass flow rate. We have information about the mass input and we need to calculate the mass output, but we have no data about the mass accumulation. With no information provided in the first part of the problem to suggest mass accumulation, we can make a reasonable assumption that the system is operating at steady state and no mass is accumulating. Next, we use the appropriate mass representations. So we get the equation mass of each car times the rate of cars entering the bridge is equal to the mass of each car times the rate of cars leaving the bridge. We can cancel out the common factors on both sides of the equation for simplicity. Considering our basis, we can rewrite this as number of cars entering the bridge per minute is equal to number of cars leaving the bridge per minute. Since the entry gate lets in one car every time it opens, number of times the entry gate opens in a minute is equal to the number of cars leaving the bridge per minute. The interval between each entry is given by the distance traveled divided by the car's speed. How many of these intervals can fit in a minute? The number of times the entry gate opens in 1 minute is obtained by 1 minute divided by the interval. We can substitute the numerical values with units. Conversion factors are required. Computing this gives us the rate of cars leaving the bridge. We can now scale it up to match the requirements of the problem. For the second part of the problem, let's write the mass flow rate balance for the total system. In this case, it is explicitly stated that there are cars parking on the bridge. The system is accumulating mass and a steady state assumption is not valid here. The mass accumulation is equal to 10% of the mass input. We follow the same steps as the previous part and obtain the number of cars leaving the bridge per minute. Finally, we scale up to match the problem requirements. Now you might be thinking that the mass of the cars did not play a role at all and we essentially balanced just the number of cars.
The problem could have skipped the mention of the mass of cars and nothing would have changed. We have talked about the flow of mass which occurs across a continuous space and over a continuous time, giving us a stream. But mass itself can occur in discrete quantities like a single car, an ice cube, a particle, or an atom. If the mass within the entity is conserved, that is, the entity is not losing or gaining mass, and if all the similar entities have identical mass, as we saw in this problem, the mass cancels out in the material balance equation, giving us a particle balance or a balance of the object count. This is not a new independent law, but a direct consequence of the fundamental law of conservation of mass. And if the problem would have skipped the mention of the mass of cars, we would need to assume that all the cars are identical with constant mass. Could you solve these problems correctly on your own? Do you feel more confident about material balances? Share it in the comments. Let us know if you have any questions. As a new channel, we welcome suggestions on how we can help you more. Your feedback is very important to us. If you found this video helpful, hit the like button and subscribe to Exemplify to help us grow and to power up your learning. See you in the next one.